Okay, so let's get started. Sorry for the delay. So welcome to the workshop on, I think the workshop organizers, Ryan, Andrew, and Mary put up succinctly hypergraph problems via global queries. I'm the partner of Chakrabarty, and my co-organizer is Shagnik, sitting there. Uh, so before I begin, so the speakers' pictures are here. They're all the program is on the website. I would like to begin with a thanks to all the speakers who agreed to give a talk here. I look forward to learning a lot from this. So before I sort of start the talk today, let me sort of say where this thing falls. It sort of uh, falls under this query access model for algorithms, where you're accessing this input via certain allowed queries. You cannot read all of it. And you want to solve some algorithmic problems on it. The focus usually is on the query complexity of how many questions that you can ask to solve your problem. And the nice thing about is that you can actually prove a matching upper and lower bound. So that's one of the things that is intellectually pleasing. So what is global queries? So before that, global queries, before I define, I'll not even try to define it, but sort of give a feel of it's queries that are not local. So local queries are something that have been studied, especially in the area of sublinear algorithms. For graphs, you basically can get a random vertex or a random edge, and after that, you can query some things which are local to that vertex or an edge, like the degree or get to a nearest neighbor, etc. And then you want to solve problems based on these query models. And sort of the way broadly global queries I like to think about it is, again, taking graphs as an example of you know the vertex set, and you can query some information about subsets of vertices. Okay? You can get some coarse information about subsets of vertices, and for maybe paying just unit cost, and you want to solve algorithmic problem based on that. Now, what kind of queries? Well, there are many kinds of queries that have been studied, and we'll see some right now, but just to get us started, for example, you can take a subset of vertices and ask, is there any edge present in this subset? Is it an independent set or not? Or you can ask, how many edges are present in that subset? Or you can ask, what is the size of the cut set? So how many edges leave that subset? And in particular, this second bullet point is an example of something called submodular function, which sort of is interesting. So we'll come to that in a bit. Or you can ask, like, given 2 points, what is the shortest path in that thing? That's something that will take you time to compute, but maybe you can get that at unit cost. So these are the things that you can get, which we will be calling global queries. And you want to sort of solve algorithmic problems based on that. Okay, so why would you like to study this? So various reasons, but maybe sometimes that's the only way to access the object that you're studying.
Oh, did I do that? I did do that. I was trying to help you with the lights and I made a mistake.
So they unplug the projector.
Yeah, give me one
Okay,
second.
so while the projector comes on, just let me try to say, why would you like to study these things? So maybe one reason might be that's the only way you can access the graph. For example, map, you have the shortest paths. You still want to figure out what the topology of it is. Maybe you can figure out the effective resistance between 2 points. You want to figure out the graph, underlying graph. Other reason is maybe it sort of modularizes our thought where the hardness of a problem is. It teases out the complexity of a problem. The third bullet point is something that I mentioned earlier, that again, for people who know submodular functions, it's a discrete optimization problem of trying to minimize a submodular function, where it is a query access model problem. And some graph problems that we'll look at today are special cases of this. And sorry, it tells you how to give more understanding of these problems. But more interestingly, maybe it sort of has connections to various other areas of TCS, sketching, streaming, et cetera. And we'll see these things in this workshop. And maybe just it's because these are very clean problems and a fun way to work on them. So that's maybe the reason. Okay, so the considerations in any query access model problem is the following. We will be focusing on the query complexity, how many questions that you need to solve the problem. That's one thing that will be, in some sense, the main consideration. The other thing that we'll look at in this many talks in this workshop are adaptivity. So how many times you have to ask these questions, get answers, and ask questions again. So this sort of adaptivity or round complexity of these algorithms is another consideration. Whether the things is randomized or is it deterministic, that's another consideration. And finally, time efficiency. So you got the answers, and you want to solve the problem, do you take polynomial time? Do you take exponential time? Do you take linear time? That's another consideration. So there are various considerations for many of these problems, and you can imagine that there are lots of questions that come out of this which require understanding. Okay, so in my talk, what do I plan to do? Oops. So I'm going to try to give an incomplete survey. It has to be incomplete because there's a lot of work here. And using these examples, I would like to sketch some techniques that will be used by various people even today and people who will speak later in the workshop. And I'll start with basically classic works, which many of you might be aware in this room, which goes back to the 40s and 60s. And then I'll talk about some work on graphs. So the classic work is not going to be about graphs at all. It will be about, we'll see what it will be about. Then we'll move to graphs, and the focus in the 90s, late 90s, was on graph learning. So you want to reconstruct the whole graph. And we'll see how the works from the classic works actually lead to these algorithms. And finally, I'll brush on some things which was started more recently on how to not maybe reconstruct the graph, but solve graph problems without reconstructing. So it could be with fewer queries. And I will mention maybe 2 works and set the stage for the talks by Louis and Shagnik that I'm going to come. So again, it's sort of a tutorial, and in the workshop, I believe this will be informal. So if there's any question, please sort of raise your hand and ask the question. Don't feel shy. And I'll hopefully be able to see it through this blazing light. So I was before coming here, I was visiting the national park, and I bought a hat for the sun. I think that is something that is advisable to the remaining speakers. Sorry. Okay. So let's begin. So we're going to talk about, for the first, maybe the next 10 to 12 minutes, about reconstructing vectors. Okay? So the unknown object here is an n-dimensional Boolean vector. And we're going to look at 2 query models. And each of these query models will take a subset of these coordinates. And either I will tell you whether the subset hits the support of the vector. So if there is at least one coordinate which is 1 that is in this subset, or no. And this is the setting of group testing. Okay, so this was studied in the late 40s, where xi equal to 1 means like a bad blood sample, and a subset of blood is something where you can test and detect if there is some sample in this that is bad or not, and you wanted to figure out all the bad samples. So that was the reason why this problem was studied, but this has been studied a lot. The second setting is you get more information from a query. Given a subset of these coordinates, you get to know how many ones are there. So you get to see summation xi I in S. And this is called the coin weighing problem in the literature. So again, the xi equal to 1 is a defective coin, and you can put it on a balance, and you get to know how many coins are defective in the sample. So that's the coin weighing problem. It was studied from the 60s. And the goal in both of these things is to find all the bad, or xi equal to 1, so reconstruct the whole vector. I would point out that in the sum case, this question makes sense even when the vector is weighted. So if you get, like, instead of being a Boolean vector, it's a weighted vector, you can still ask the question, can I reconstruct this vector using sum queries? The first one only gives Boolean answers, so you cannot reconstruct the weights by that. Okay, so these are the classic questions. So let's start with group testing, where you only get to know if I hit the support or not. So already you can see if nothing else is known, you need n queries, right? Why? Because and this is sort of the thing in blue that I'm saying is one of the basic ways of proving lower bounds in this model. Every query gives you at most 1 bit of information, because it's yes or no. And there are 2 to the n possible vectors. So if I take a random vector, that's n bits of uncertainty. And so you need n queries just from an information theory argument to reconstruct the vector. So what people focus on is on restricted class of vectors. And one restricted class that has been studied a lot is when I tell you that the vector has at most d ones. And in that case, if you do the same argument, you basically need roughly d log n queries to reconstruct the vector, because there are roughly n choose d many vectors possible, again, using the information theory argument. So d log n is the sort of easy lower bound barrier. So let's look at some, so let's sort of warm up. So D equal to 1 case. So here is a technique that everybody knows in this room, binary search. And this is going to be a very useful technique in this, this sort of many class of problems. So using binary search, you can easily find if there's only one bad, like if there's only one bad sample or xi is equal to 1 for only one I, you take an arbitrary half, and if you check if it hits the support, if it hits it, you recurse on it, otherwise you recurse on the complement. Okay? This takes log n many queries, which is optimal, but the problem with this is that it is extremely adaptive, right? You have to proceed in log n rounds. So the next tool is what sort of is called, I call it non-adaptive binary search, that you can actually solve this problem in log n queries in just one round. And the way you do it, as an again, it's a nice exercise if you have not seen it, but the way you do it is you can think of it connection to, so coding theory. So you write the numbers 1 to n in binary as columns of a matrix. And then what you query are sort of the rows of this matrix. So for example, in the first row, it says you have ones in the right half. So you're taking the right half of these. That's the subset that you query. The second row says 2, 3, and maybe 6, 7. Those are the things you query, et cetera, et cetera. So that's the meaning of this matrix. So you are making log n many queries, and you basically do it in one shot. It's in one round. And the main sort of reason why this works is if there's only one 1, for example, if that fifth coordinate is 1, then the corresponding column is going to tell you, so the answer pattern for that column is going to tell you which is the entry, right? So for example, if the fifth column is 1, then that column is 1, 0, 1, which means the first test will say yes, because that hits that subset. The second column will say no, the third column will say yes. So the answer pattern, you just convert it into decimal and it'll tell you which coordinate has the 1. So this is a one non-adaptive. If you've not seen it, it's a pretty cool trick. In log n queries, you can get it. So D equal to 1, you have a very simple non-adaptive optimal algorithm, which is the best of all possible worlds. So what happens with general D? Well, if you don't care about adaptivity, you can just find one coordinate at a time. So you can do it in D log n, which is the optimal thing, but it is adaptive. So can you do it non-adaptively? Can you do it in much fewer rounds? And the answer is yes. So for example, so that brings to another tool we'll see a lot in this thing is just random sampling. It's our bread and butter tool in TCS. So if my support has D entries, then if I just sample at rate 1 by D every coordinate, right? So if I take a subset where every entry is present with probability 1 by D, there is a constant probability that I'll hit none of these samples or I'll hit just one of these samples. And intuitively, you can boil down to the D equal to 1 case on that sample. So that's a technique that is very useful. So just to sort of, spend a little time on this, if you sample a subset, K subsets, where each subset contains I with probability 1 by D, and you query it, and if you see a no, if you see that I have not hit the support, you immediately know that all of them must be zeros. So zero out all the coordinates which participate in a no query, and the rest, you just say they are all defective. Okay? So maybe you say that you say more than D things are 1, etc., but that's the algorithm. Okay? K is not specified, but we'll see what K is in a minute. So there are no false zeros that are reported. So if xi is equal to 1, we report 1. We'll never report something which is defective as non-defective, because it will not participate in that no query. And if xi is equal to 0, well, let's think about it. So I take a sample, one of these samples, and let's see what's the probability that this sample will certify that this coordinate is 0. So to certify that, first I need to pick that I in my sample. So that's probability I is in R. And I should not pick any of the ones in my sample. If that happens, then I will definitely say this I was equal to 0. I'll zero it out. So the probability that I is in R is 1 by D. The probability that none of the ones are in R, this is where the 1 by D sampling comes in. I go over all the d coordinates. I don't pick them with probability 1 minus 1 by d. So the probability that I don't pick any of them is 1 minus 1 by d to the d, which is a constant. So basically, it says that for any coordinate that is 0, a single sample will zero it out in the second step is at least with probability 1 by 4d, omega 1 by d. Which means that if I take d log n by delta many samples, if k is like d log n by delta, then with probability 1 minus delta uni bounding over every I that is 0, I will actually reconstruct the vector. Yeah, so that's the simple random sampling algorithm. It's non-adaptive. It is polynomial time. And what it gives is a d log n by delta query non-adaptive randomized algorithm which succeeds with probability 1 minus. Good. So now, how many vectors are there which have at most d1s? There are only n choose d vectors. So if you bring this delta probability, the error probability below 1 by n choose d, then just by union bounding, you can argue that there exists a set of d, so d log n by delta, where delta is roughly 1 by n to the d. So around d square log n, there exists d square log n many queries that you can make, so that their answers will determine every x, which has at most d1s. Okay? So this simple randomized algorithm gives an existential theorem. It says there exists a d square log n non-adaptive set of queries. Of course, where they are, it does not tell us. And even if you found them, how to decode the answers, it does not tell us. So those are not clear. But it at least tells you that there are d square log n many queries out there for any n and any d. And indeed, there are actually explicit constructions using connections to coding theory, and they're also efficient. And these are non-trivial work. So there exists a polynomial time algorithm which for any n and d can find this sort of set of queries which are d square log n many and which are also efficiently decodable. So this was a result by Porat and Rothschild from 2006. So at this point, maybe I will mention one big open question in this area. It's been long-standing. So this d square log n for non-adaptive is not a lower bound. The lower bound is d square log n divided by log d. And it's not known if even existentially this log d can be removed or not, or can a better lower bound be proved. That's something that it's worth mentioning. But this is a very old open problem. Okay. So let me move to coin weighing. So remember, what was coin weighing? In coin weighing, I have more information from every query. And not only I get whether I hit the support or not, I actually get how many elements of the support I hit in this subset S. And again, the goal is to learn X. Again, there's a set of works in the 60s that was stated. And again, let's apply our information theory argument. Again, there are n bits of uncertainty. But now every query is giving a number between 1 and n. So potentially it's giving me log n bits of information. And so the information theory argument says I need at least n by log n to the base 2 many queries. Yeah? So it's not n, it's now n by log n. And what is, I think, fascinating is that this is tight. So there is an algorithm which makes 2n by log n, again, log n to the base 2 many queries. And in fact, this is non-adaptive. And furthermore, for non-adaptive algorithms, you can tweak that information theory argument a little bit to show that 2n by log n is also tight. So this problem, coin weighing, is tight for non-adaptive algorithms. So let me say what I mean by this, the fact that this 2n by log n suffices, because this is a tool that is going to be used in the graph setting as well. So what I mean is that there exists a matrix. Oh, sorry. Yeah. If D, okay, so the question was if D is 1, how many bits of information? So I should have clarified. I'm now making no restrictions on the Boolean vector. X can be any of the 2 to the n vectors. But we will come to the D thing in the next slide. Good point. Okay, so what I meant, what does this mean is that there exists a matrix, an L cross N matrix, which again should think of the rows being the coordinates that I'm querying. So that if you just look at AX, from AX I can determine X. Now this statement as is actually not difficult to prove by the probabilistic method. In fact, it's a nice argument. It takes a little bit of work, but it's a nice exercise. But this algorithm, so the construction of this matrix by, so there were the last two, Cantor, Mills, and Lindstrom actually gave explicit constructions and efficient ways of decoding and almost linear time algorithms to decode. And I'll not talk about them, but they're based on very, very nice ideas from Fourier analysis where you think of every column as a function in L dimensions. So I'll not say more about this in this talk, but it's a very nice construction. Okay, so basically n by log n is needed. 2n by log n, there's a non-adaptive, deterministic, fast algorithm. And this gap between 2 and 1 is actually a big problem in this coin weighing literature. So we don't know if adaptivity helps here up to this factor 2. Again, you may or may not care for this factor 2, but this is a problem that is been open since 60 years. Okay. But now let's come to the question that was asked. What if I knew more about this vector? What if I knew that support was at most D? Oh, this is going to be a tool that is going to be used. So if X has at most D once, now the lower bound is not n by log n, but it is, well, it is whatever it is. It's log of n choose D by log D. And indeed, again, there is a probabilistic method argument which shows that D, so log n choose D by log D queries suffice, maybe with some constants that are there, I forget, maybe even the constant is tight. So there are algorithms, there's an existential proof of D log n choose D by log D. And if you allow adaptivity, then in fact this can be obtained via polynomial time algorithms. So you can reconstruct in D log n by D by log D query efficient adaptive algorithms. Non-adaptive efficient algorithms is still an open question in this world. And more is true. So again, this is for the Boolean vector case. As I said, the coin weighing problem makes sense even if the xi's were not 0, 1, but any weights. So if the weights are non-negative, and I tell you that the support is at most D, you can get the same query complexity by a randomized adaptive algorithm. So this is a result from maybe much more recent, from 2013. The weights need to be non-negative. If the weights are allowed to be negative, then actually you cannot do much. And this is again an algorithm. Maybe Safar will talk about it when we talk about lower bounds for connections to disjointness and communication complexity. But the weights need to be non-negative. Okay, so that sort of summarizes the classic works. I don't know how much time I have. I'll keep talking till, and we'll smoothly hand over to Louis here, okay? So let me go a little faster. So graph learning. And the setting is, again, I have an unknown graph. I know the vertices V, and I am allowing a couple of, so some sort of queries here. And the one query is the independent set query. You can, again, query a subset, and I'll tell you whether there are any edges in that subset or not. Additive queries tells you how many edges are there in that subset. And the thing that sort of drew me into this area is the cut queries, where I can tell you how many edges leave this subset. So have one endpoint in the subset and one endpoint outside the subset. And this function, this cut function, S to delta S, is a special case of something called the submodular function. If you don't know it, that's fine. But minimizing submodular functions is a problem that is a big problem in discrete optimization. But anyway, so the graph learning people wanted to know, so this is I think the first reference that I am aware of is a paper by Rubinstein and Kucherov. These were computational biologists, and these problems arose from that area. They wanted to reconstruct the edges of this graph, to reconstruct the whole graph. Okay, so let's make a few observations. First, these independent set queries and additive queries generalize the group testing and the coin weighing problem. Just if you think about the star graph, right? If I promise you that the graph is a star where some edges might not be there and some edges are there, and you need to find which edges are there. So those are special cases of this because you can think of the vector, a 0, 1 vector indicating whether I have an edge from the center to the various leaves or not. The second observation is in graphs, the cut query, which says how many edges leave out, and the additive queries, which says how many edges are within, they're basically equivalent if I knew the degrees of the graph. Because if I knew the degrees of the vertices, then the sum of the degrees is 2 times the additive query plus the cut query. So these are, in graphs, these are equivalent. The second observation, this observation takes a little bit of time to think, is this fact that I can go vertex by vertex and try to reconstruct the edges that are incident on them, says that if I use coin weighing ideas, then I can actually learn the graph. I can learn the incident edges for every vertex. I apply the coin weighing algorithm for every vertex. I pay n by log n for every vertex. There are n vertices, so n square by log n add or cut queries suffice to learn the graph. Note that the obvious thing would be to go over every pair and ask, are you an edge, are you an edge, are you an edge? So n square is the obvious thing. You can shave off log n. And if you know nothing else about the graph, this is optimal, because there are 2 to the n square many graphs, and you get only the cut value, which is the number between 1 and n square. So the focus on this in this world has been if my graph is sparse. If I tell you that the graph has only m edges, can you tell me what the complexity is? And again, by an information theory argument, with independent set queries, the lower bound is m log n, and with cut queries, it's m log n by log n. Okay, so I wanted to show you one algorithm. I'm thinking so should I show the independent set or the cut query? Since this is first, let me show you how to reconstruct the graph in m log n queries with independent set. So again, I can query a subset and I know it's independent or not. Now, one thing to note is I cannot use this vertex by vertex viewpoint, because suppose I want to know if there is an edge from the top vertex to the green set. I cannot make an independent set query, because an edge between the vertices in the green set will always say, no, the subset is not independent. So one needs to sort of be more clever, and there's a very nice algorithm of Angluin and Chen which gives it. So let me describe this. So I have independent set queries. I want to reconstruct the graph. So I halve this. I recursively learn both halves. And now there are only m edges, which means that the graph can be colored in root 2m colors, okay, 2 root m colors. Why? This is a nice exercise. I'll let you guys ponder about maybe after the workshop. But once you have a low coloring with only root m colors, it basically says I've got these pink blobs which are independent, the different color classes, and there are only root m many blobs like this. So I can take root m times root m. I can ask whether the blob players are independent or not. In particular, I can figure out which blobs have edges between them. For example, the first blob on the left and the first blob on the right, I find that they're not independent together, so there are some edges between them. And once you have 2 independent sets, then I can actually apply the vertex neighborhood idea and the group testing ideas to learn every edge between any pair of blobs, paying log n per blob. Okay? Again, you'll use binary search and etc., so I'll not go into that. So altogether, you pay m queries to figure out which blobs are interesting, which pair of blobs are interesting. There are log n many such levels, so you pay m log n, and then you pay log n per edge. So that's how you get an m log n. So again, the tools that are used for this algorithm is the tools that arose in coin weighing, group testing and coin weighing. Okay, so the same situation is true for when you have add queries or cut queries. You can use the ideas from coin weighing to actually get the m log n by log m. So whatever was information theoretically optimal, the lower bound, you get it using the idea from coin weighing to deconstruct the graph. Again, I would have liked to tell you one of these algorithms, but I think I will skip this. in the interest of time, and I will move to I'll move to hypergraphs for a bit. So in the hypergraph world, again, the unknown object is an undirected hypergraph. And again, you can ask the same set of queries. You can ask, given a subset, is there a hyperedge completely contained in that? That's the edge detecting query. Additive is how many hyperedges are completely contained in that. The cut queries are slightly different. It says how many hyperedges cross this subset, which means has some. So hyperedge is now a subset of vertices, has something inside the subset and something outside the subset. And that's a submodular function. And again, the goal is maybe to reconstruct the hypergraph. So this is, again, work that Nguyen and Chen started in a different paper. And now, one thing that I want to point out, which sort of segs into the other talks, is that in hypergraphs, the additive and cut queries are not equivalent. Because the degrees, because of non-uniformity and various other reasons, you cannot sort of, just from the degrees and the additive set, you cannot figure out what the cut set is or vice versa. In fact, the situation is worse. With cut queries, you cannot hope to reconstruct hypergraphs because there are, for example, this is an example of two hypergraphs. One is a normal graph, one is a hypergraph, where the cut profile is the same. So you make all the 2 to the n cut queries. They have the same answer in both the hypergraphs, but they are different. So you cannot reconstruct the hypergraph using just cut queries. On the other hand, you can reconstruct the whole hypergraph, an m-edge hypergraph, in mn log n additive queries. And this is a, well, I say exercise, but this is actually a paper of Nguyen and Chen. This is a nice algorithm. So additive queries and cut queries are vastly different in the hypergraphs. Okay, so let me sort of end with the things that have been recently happening, where you don't want to maybe reconstruct the graphs or the hypergraphs, but only want to discern some properties using these algorithms. So in ITCS 2018, there were 2 papers which sort of, coincidentally came out studying these things. So one was a paper by Beame et al., where they looked at the model of this independent set queries. I query a subset, and I want to know if the set is independent or not. And their goal was to estimate properties, like estimating the number of edges. So we're not going to talk about these things in this workshop, but this is a lot of work that has happened on this, trying to figure out how many queries do you need to do this. By some of the works by people in this room. But we had to choose what kind of talks to give. So we are not going to talk about this, but I wanted to mention that these exist. The thing that we'll talk about more in this set of 2 talks that are coming up is this work by RSW, Rubinstein, Sham, and Weinberg, where they looked at cut queries. Again, given an S, I want to know how many edges exited, which is the same as additive queries. But their goal was not to reconstruct the graph, but to return the minimum cut of the graph. And why? Because this is a special case of something called the symmetric submodular function minimization problem, which is a classic problem in discrete optimization, whose query complexity is still unknown. In fact, this is the state of the art. We know that on an n-element universe, you can minimize a submodular function in roughly n-square queries. So in particular, you can solve the minimum cut in n-square queries, but you can reconstruct it. So that's not maybe interesting for the graphs, but for hypergraphs it is. And furthermore, if you want, so the state of the art right now is that the n-square queries, the algorithm itself, after seeing the query answers, is not polynomial time. If you want efficient algorithms, then the situation is cubic. There are n-cube time algorithms to solve any submodular function, minimize the submodular function. On the other hand, the best lower bound is still linear or near linear. So there is a gap there, and what RSW are interested in is actually for graph cut, for the special case, can you actually get maybe better than quadratic algorithms? So that's the kind of work that RSW started. And this table sort of gives the brief lay of the land, where the answer for undirected, unweighted graphs is yes. So you can get actually the global min cut in linear number of queries, the randomized algorithm. There's no log n there. But if you look at ST min cut, and this is a talk that we'll hear more tomorrow, we can have subquadratic algorithms, in fact, into the 3/2 algorithms, not only ST min cut, but more. So there has been progress, and we'll hear about them in coming talks. The thing that I wanted to sort of leave with is that certain settings we are far from we don't know what to do. So in particular, directed graphs, we cannot breach this n square thing apart from maybe a log n by using coin weighing ideas. Even to detect if a from S to T, is it connected? We don't know of a subquadratic algorithm. And this is a very clean question. So I have directed cut queries, which given a subset tells me how many edges leave the set or come into the set. I'll give you both. You just have to determine whether there's a path from S to T. We don't know anything better than n square, which basically reconstructs the whole directed graph in a certain sense. Hypergraphs are also open, where I don't know of anything which is better than using the hammer of submodular function minimization directly. So, okay, so with that, I will hand over to Louis and Shagnik. Thank you for your attention. And I'll take questions maybe while Louis sets up.